Wondered if you fell into a black hole, would time stop? Picture a cosmic entity so incredibly massive and dense that it bends the very fabric of space and time. Black holes, the universe's enigma, are such entities. They're not just fascinating, they're crucial to our understanding of time itself. How does this celestial giant affect the ticking of the cosmic clock? Do black holes slow down time, or do they bring it to a halt? Today we embark on a journey to unravel this cosmic mystery. To understand the effect of black holes on time, we first need to grasp what black holes are. Let's embark on this cosmic journey. Born from the remnants of massive stars, black holes are one of the most intriguing phenomena in the universe. When a star much larger than our Sun exhausts its nuclear fuel, it undergoes a dramatic collapse under its own gravity. This implosion results in a supernova, a stellar explosion that briefly outshines an entire galaxy. What's left behind is an extremely dense core. If this core is above a certain mass, known as the Tolman-Oppenheimer-Volkoff limit, it will continue to collapse into a singularity, giving birth to a black hole. Now, what makes black holes fascinating is their unique features. The point of no return surrounding a black hole is known as the event horizon. It's the boundary beyond which nothing, not even light, can escape the black hole's immense gravitational pull. Hence the name black hole, as it absorbs all light and reflects none. But black holes aren't just cosmic vacuums. They're a lot more complex and interesting. Their gravity is so strong that it warps and distorts space and time, a concept we know as space-time curvature. This is based on Albert Einstein's theory of general relativity, which tells us that what we perceive as gravity is actually the curvature of space and time caused by mass and energy. It's also worth mentioning that black holes come in different sizes. Stellar black holes, the ones formed by collapsing stars, are incredibly dense and can be up to 20 times more massive than our Sun. On the other hand, supermassive black holes found at the center of galaxies can be billions of times the mass of our Sun. Black holes are cosmic behemoths, bending the very fabric of space-time. They're not just distant cosmic monsters, but key players in the grand cosmic ballet, influencing the birth and death of stars and galaxies, and maybe even the passage of time itself. Stay tuned as we delve deeper into the gravitational clutches of these astronomical entities. Now let's delve into the concept of time dilation. This intriguing phenomenon, central to our understanding of black holes, is a direct result of Einstein's theory of relativity. This theory, in essence, revolutionized our understanding of space, time, and gravity. You see, Einstein proposed that space and time are not separate entities, but rather interwoven into a four-dimensional fabric known as space-time. Now imagine space-time as a rubber sheet. When a massive object like a star is placed on this sheet, it creates a curvature, a warp, if you will. This is what we perceive as gravity. The heavier the object, the deeper the curve, and the stronger the gravitational pull. Now here's where it gets fascinating. This warp in space-time doesn't just affect space, but time as well. According to Einstein, the stronger the gravitational field, the slower time passes. This is known as time dilation. So if we consider a black hole, one of the most massive objects in the universe, it creates an incredibly deep warp in space-time. The gravitational pull near a black hole is so immense that it can slow time to a crawl relative to weaker fields. To put this into perspective, if you were to hover near the event horizon of a black hole where gravity is at its most extreme and somehow survive, time for you would pass much slower than for someone far away from the black hole. A minute for you could equate to years, even decades for them. This concept might sound like science fiction, but it's a reality predicted by the math of Einstein's theory, and it's been verified by numerous experiments and observations. So in essence, close to a black hole, time ticks slower. This is one of the most mind-boggling consequences of gravity and its effect on time, a concept that continues to challenge and captivate us as we further explore the mysteries of our universe. Imagine falling into a black hole. What would happen to time? As we dive deeper into the heart of this cosmic beast, we must first understand a bizarre phenomenon known as spaghettification. This is a term coined by the scientific community to describe the stretching and squeezing effect caused by a black hole's intense gravitational pull. As you approach the black hole, the gravitational pull at your feet becomes much stronger than at your head, stretching you out like a strand of spaghetti. But remember, this is all from the perspective of a distant observer. If you were the one falling into the black hole, you wouldn't notice any such change. You'd feel perfectly normal with no stretching or squeezing. That's the strange thing about black holes. They distort not only space but also our perceptions. Now let's talk about time. Time, as we understand it, is a part of the fabric of the universe, intertwined with space to form what we call space-time. A black hole with its immense gravity warps space-time to such an extent that it creates a sort of funnel, with the black hole sitting at the very bottom. As you fall into this funnel, from your perspective, time would seem to move normally. But to an observer watching from a safe distance, your fall would appear to slow down the closer you get to the event horizon, the point of no return. And here's the truly mind-boggling part. To this observer, you would never quite seem to reach the event horizon. Instead, you would appear to slow down more and more until you're essentially frozen in time. This is due to the extreme gravitational time dilation near the black hole. Time, as perceived by the distant observer, virtually comes to a standstill at the event horizon. Thus, in the eyes of an external observer, you'd appear frozen in time at the event horizon. So, in a sense, falling into a black hole is like falling into forever, a journey where time loses its meaning and eternity takes on a whole new perspective. One might ask, does this mean black holes could be used for time travel? A question as intriguing as it is complex. Let's delve into the theoretical possibility. Black holes, with their immense gravitational pull, warp the fabric of space-time profoundly. This warping, according to Einstein's theory of relativity, could theoretically create what we call wormholes, shortcuts through space-time that could be used for instantaneous travel across vast cosmic distances and potentially through time itself. But before you start packing your bags for a temporal vacation, it's important to note that the reality of such travel is likely far more complex and less feasible. The extreme gravitational forces near black holes would wreak havoc on anything or anyone daring enough to venture near. We're talking about tidal forces strong enough to stretch you into a thin stream of atoms, a process rather unpleasantly referred to as spaghettification. Moreover, even if we could somehow survive this journey, there's no guarantee we'd end up where or when we'd want. Theoretical physicist Kip Thorne suggests that any wormholes near black holes would be highly unstable, potentially collapsing the moment any matter tries to pass through. Furthermore, the laws of physics as we currently understand them do not allow for backwards time travel, only forward. So while you might get a head start on the future, there's no going back. While enticing, the idea of time travel using black holes remains a topic of speculation and debate. In this journey through the cosmos, we've unearthed some fascinating concepts. We've delved deep into the mysterious realms of black holes, these cosmic chasms that bend not just space but time itself. We've discovered their nature, these enigmatic entities born from collapsed stars, so dense that not even light can escape their grasp. We've explored the effects they have on time, how the immense gravitational pull slows time down, making seconds stretch into potentially infinite moments. We've touched on the concept of spaghettification, a rather whimsical term for the extreme gravitational effects experienced by objects falling into a black hole. And finally, we've ventured into the realm of the theoretical, exploring the tantalizing idea that black holes could possibly be gateways for time travel. A concept that, while not yet proven, continues to ignite the imaginations of scientists and enthusiasts alike. While black holes continue to baffle us, one thing is clear: they're a testament to the wondrous complexity of our universe.